Greetings, curious humans. Welcome to a scintillating episode of Cosmic Chronicles with your friendly science educator AI, SciBotGPT. Today, we embark on an astronomical adventure to explore the radiant superstar of our solar system, the Sun. Get ready to witness the captivating secrets of our fiery friend as we delve into its awe-inspiring layers, from the blazing core to its enigmatic surface. Brace yourselves for a cosmic roller coaster ride filled with magnetic marvels, mesmerizing sunspots, and jaw-dropping solar flares that outshine any fireworks show. So, fasten your seatbelts and prepare to be starstruck. Join us as we unravel the mysteries of the Sun, the celestial spectacle that illuminates our world like no other. Welcome to the Sun, where science and wonder collide. Let's dive in. The Sun, a nearly perfect ball of hot plasma, is the radiant star at the center of our solar system. It generates energy through nuclear fusion in its core, emitting light, ultraviolet, and infrared radiation, making it the primary source of energy for life on Earth. With a radius 109 times that of Earth and a mass 330,000 times greater, the Sun dominates our solar system, comprising 99.86% of its total mass. It consists mostly of hydrogen, about 73%, and helium, about 25%, along with traces of other elements like oxygen, carbon, neon, and iron. Formed approximately 4.6 billion years ago from the collapse of matter in a molecular cloud, the Sun is a G-type main sequence star, often called a yellow dwarf, though its light is white. It initiated nuclear fusion in its core, where 600 million tons of hydrogen are fused into helium every second, releasing a tremendous amount of energy. This energy takes thousands of years to escape the core and becomes the source of the Sun's light and heat. As the Sun evolves, it will eventually transform into a red giant, expanding and engulfing the orbits of Mercury and Venus, rendering Earth uninhabitable in about 5 billion years. After shedding its outer layers, it will become a dense, cooling white dwarf, no longer producing energy through fusion but still emitting heat and light. The Sun's impact on Earth has been recognized since ancient times, with some cultures considering it a deity. The synodic rotation of Earth and its orbit around the Sun form the basis of solar calendars, including the widely used Gregorian calendar. In summary, the Sun is a magnificent and vital star, illuminating our world and playing a crucial role in sustaining life on Earth. The English word sun traces its origins back to Old English sun. Similar words can be found in other Germanic languages and Indo-European branches, all stemming from the Proto-Germanic sunnen. The word for sun in most Indo-European languages typically has an L sound, while the Germanic languages use the genitive stem with an N sound. The Sun is often described with the adjective sunny for sunlight and solar in technical contexts, derived from the Latin word sol. In poetry and science fiction, the Greek word helios and the Latin word sol are sometimes personified as the Sun. In planetary astronomy, sol with a lowercase s is used to refer to the duration of a solar day on other planets. The English weekday name Sunday comes from Old English Sonnendag, meaning sun's day, which is a Germanic interpretation of the Latin phrase dies solis and the Greek phrase hemera heliou, both meaning day of the sun. The astronomical symbol for the Sun is a circle with a center, used to represent units such as solar mass, solar radius, and solar luminosity. The Sun is a G-type main sequence star, accounting for about 99.86% of the solar system's mass. It is brighter than the majority of stars in the Milky Way and classified as a population 1 star, rich in heavy elements. The Sun's formation may have been influenced by shockwaves from nearby supernovae, resulting in a high abundance of heavy elements observed in the solar system. With an apparent magnitude of -26.74, the Sun is by far the brightest object in the Earth's sky, outshining even Sirius, the next brightest star. It is located at an average distance of about 150 million kilometers, 93 million miles, from Earth, with slight variations due to Earth's orbit. The Sun's energy, which reaches Earth in approximately 8 minutes and 20 seconds, sustains life through photosynthesis and influences the planet's climate and weather. Although the Sun doesn't have a distinct boundary, its density decreases exponentially as we move away from the photosphere, which is considered its visible surface. The Sun is nearly spherical, with a slight oblateness of approximately 10 kilometers, 6.2 miles, between its polar and equatorial diameters. It experiences differential rotation, rotating faster at the equator than at the poles, influenced by convective motion and the Coriolis force. From Earth's perspective, the Sun appears to have a rotational period of about 28 days at its equator. In summary, the Sun is a remarkable star, providing immense light and energy to our solar system, and its characteristics, including its formation, brightness, distance, shape, and rotational behavior, contribute to its uniqueness and influence on Earth. The Sun primarily consists of hydrogen, 74.9%, and helium, 23.8%, with heavier elements making up less than 2% of its mass. Oxygen, carbon, neon, and iron are the most abundant among the heavier elements. The Sun's original chemical composition was inherited from the interstellar medium, with hydrogen and helium produced during the Big Bang nucleosynthesis. The heavier elements were created by previous generations of stars and spread into the interstellar medium through stellar processes such as supernovae. Over the Sun's 4.6 billion-year lifespan, hydrogen has been continuously fused into helium in its core, gradually increasing the proportion of helium. Some helium and heavy elements have settled towards the center of the Sun due to gravity. Heat is transferred by radiation, and the fusion products remain in the core. As a result, an inner core of helium has formed. The current photosphere shows a reduced helium fraction compared to the protostellar phase. In the future, helium accumulation in the core will cause the Sun to evolve into a red giant in approximately 5 billion years. The chemical composition of the Sun's photosphere reflects that of the primordial solar system. Spectroscopic analysis of the photosphere and examination of unheated meteorites, which retain the protostellar Sun's composition, provide consistent measurements of the Sun's heavy element abundances. The core of the Sun makes up about 20 to 25% of its radius and has a high density of up to 150 times that of water. It reaches temperatures of around 15.7 million Kelvin, much hotter than the surface of the Sun. Energy is primarily produced in the core through nuclear fusion processes, specifically the proton-proton chain and the CNO cycle, which convert hydrogen into helium. About 99% of the Sun's power is generated within the core, with only a small fraction produced in the outer layers. The core is the only region where fusion reactions occur on a significant scale, and energy generated there is transferred outward through the Sun's layers. The proton-proton chain occurs billions of times per second in the core, fusing protons into helium and releasing a tremendous amount of energy. The Sun's power output is equivalent to the mass-energy conversion rate of millions of metric tons per second. Despite the high power output, the power density in the core is relatively low due to its large size and density. The fusion rate in the core is in a self-regulating equilibrium, with any deviations from the current rate causing the core to adjust its temperature and density, thus maintaining a stable fusion rate. The Sun's atmosphere consists of several layers. The photosphere is the visible surface of the Sun and has a temperature of about 5,700 K. Above the photosphere is the chromosphere, where temperatures increase gradually to around 20,000 K. Beyond the chromosphere is the transition region, a thin layer where temperatures rise rapidly from 20,000 K to about 1 to 2 million K in the corona. The corona is the extended outermost layer of the Sun's atmosphere, with temperatures reaching millions of degrees. The corona is also the source of the solar wind, a flow of plasma that extends into interplanetary space. The Sun's atmosphere undergoes significant temperature changes and exhibits dynamic behavior. The transition from the radiative zone to the convective zone is marked by a layer called the tachocline, where there is a sharp change in rotation and a large shear between the two regions. The convective zone is where the Sun's energy is transported through convection, as opposed to radiation. Convective currents carry heat from the interior to the surface, creating thermal cells and causing the granular appearance of the Sun's surface. The Sun's atmosphere is not fully understood, and many phenomena, such as the heating of the corona and the generation of the Sun's magnetic field, are still subjects of scientific investigation. The aliosphere, the outermost region of the Sun's atmosphere, extends beyond the corona and is filled with the solar wind. The aliosphere interacts with the interstellar medium and forms a boundary known as the heliopause. In recent years, space probes like the Parker Solar Probe have provided valuable data and insights into the Sun's atmosphere, including encounters with the Alvain surface and observations of the heliopause. The Sun is a G2V star with a surface temperature of approximately 5,778 K. It emits light across the visible spectrum, appearing white when viewed from space or when the Sun is high in the sky. However, atmospheric scattering can cause the Sun to appear yellow, red, orange, or magenta when it is low on the horizon. The solar radiance peaks in the green portion of the spectrum when viewed from space. The solar constant is the amount of power the sun deposits per unit area directly exposed to sunlight and is approximately 1,368 W/m superscript 2 at a distance of 1 astronomical unit from the sun's sunlight is composed of about 50% infrared light, 40% visible light, and 10% ultraviolet light. Earth's atmosphere attenuates sunlight, so the power reaching the surface is around 1,000 W/m superscript 2 in clear conditions near the zenith. Ultraviolet light from the sun has antiseptic properties but is also responsible for sunburn, vitamin D production, tanning, and skin cancer. It is strongly absorbed by Earth's ozone layer, resulting in variations of UV intensity with latitude and influencing biological adaptations such as variations in human skin color. The sun has a magnetic field that varies across its surface, with a polar field of 1 to 2 Gauss and up to 3,000 Gauss in sunspots. The magnetic field extends into space through the solar wind, forming the interplanetary magnetic field. The solar magnetic field undergoes a quasi-periodic 11-year cycle known as the solar cycle, characterized by changes in the number and size of sunspots. The interplay between the sun's magnetic field and the solar wind results in the formation of an Archimedean spiral structure called the Parker spiral. The interplanetary magnetic field is stronger than the dipole component of a solar magnetic field due to magnetic fields generated by electrical currents in the surrounding plasma. Neutrinos are released by the sun's fusion reactions, and while they rarely interact with matter, they can escape the sun immediately. The discrepancy between the predicted and observed number of solar neutrinos was resolved by the discovery of neutrino oscillation, where neutrinos change flavor before detection. Sunspots are dark patches on the sun's photosphere that correspond to concentrations of magnetic field. They appear cooler than the surrounding photosphere and can be tens of thousands of kilometers across. Sunspots are more common near the solar equator during the solar cycle's maximum phase, while they tend to form at high solar latitudes during the minimum phase. The 11-year sunspot cycle is part of a larger 22-year dynamo cycle, involving the exchange of energy between toroidal and poloidal solar magnetic fields. Sunspot pairs, with opposite magnetic polarities, emerge through the photosphere during the cycle's maximum phase. The magnetic polarity of sunspot pairs alternates with each solar cycle. Solar activity, influenced by the sun's magnetic field, leads to phenomena such as solar flares, coronal mass ejections, and the emission of high-speed streams of solar wind. These events can impact Earth, causing auroras, disruptions in radio communications, and power outages. Solar activity may also have played a role in the formation and evolution of the solar system. Changes in sunspot numbers over long periods are believed to be correlated with changes in solar irradiance, which could influence Earth's long-term climate. Historical periods with reduced sunspot activity, such as the Maunder minimum during the 17th century, have been associated with colder temperatures on Earth, including the Little Ice Age. In December 2019, a new type of solar magnetic explosion called forced magnetic reconnection was observed. It involves the explosive divergence and convergence of solar magnetic field lines triggered by an explosion in the corona. The sun is currently in a stable phase of its life and has remained relatively unchanged for over 4 billion years. It is estimated to remain stable for another 5 billion years. The sun formed about 4.6 billion years ago from the collapse of a molecular cloud, and its age is consistent with the oldest solar system material. The formation of the sun was likely triggered by a nearby supernova, causing the collapse of matter within the molecular cloud. During its main sequence stage, the sun undergoes nuclear fusion, converting hydrogen into helium in its core. This process releases energy in the form of solar radiation and neutrinos. The sun has been converting mass into energy for billions of years, with approximately 100 times the mass of Earth already converted. It will spend a total of about 10 to 11 billion years as a main sequence star before entering the red giant phase. Over time, the sun is gradually becoming hotter in its core and at its surface, larger in radius, and more luminous. This is due to the gradual shrinking of the core, allowing the outer layers to move closer to the center and release gravitational potential energy. As a result, fusion occurs at an increased rate, leading to a higher luminosity. The sun's brightness is currently increasing by about 1% every 100 million years. In approximately 1 billion years, the increased luminosity of the sun will lead to the depletion of liquid water on Earth, making it unable to support complex, multicellular life. This will ultimately result in a complete mass extinction of multicellular organisms on the planet. After approximately 5 billion years, the Sun will run out of hydrogen in its core, causing core hydrogen fusion to cease. Without the energy from fusion, the core will start contracting, releasing gravitational potential energy. This will lead to an increase in the Sun's luminosity and mark the end of its main sequence phase. Over the next billion years, the Sun will expand, first into a subgiant and then into a red giant. During the red giant phase, the Sun will expand to about 0.75 astronomical units, 110 million kilometers, and likely engulf Mercury and Venus. This phase will last for around a billion years, during which the Sun will lose approximately a third of its mass. After the red giant phase, the Sun will experience the helium flash, where the core ignites violently through the triple alpha process, converting helium into carbon. The Sun will shrink to about 10 times its current size and 50 times its luminosity. It will enter the red clump or horizontal branch, becoming moderately larger and more luminous as it continues to react helium in the core. Once the helium is exhausted, the Sun will expand again, repeating the expansion phase that occurred after the hydrogen in the core was depleted. This time, the expansion will happen faster, and the Sun will become larger and more luminous, potentially engulfing Venus. This phase is known as the asymptotic giant branch, characterized by alternating reactions of hydrogen and helium in different shells. The Sun will experience unstable periods with rapid mass loss and thermal pulses that increase its size and luminosity. Eventually, the Sun will lose its outer envelope and form a planetary nebula, with only the exposed core remaining. The core will become a white dwarf, with a temperature over 100,000 K and containing about 54.05% of the Sun's current mass. The planetary nebula will disperse in about 10,000 years, while the white dwarf will exist for trillions of years before eventually fading into a hypothetical black dwarf. The Sun is the center of the solar system, which consists of 8 known planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Additionally, there are 9 dwarf planets, an asteroid belt, comets, and numerous icy bodies beyond Neptune. The planets and many smaller bodies have their own natural satellites. The Sun is influenced by the gravitational pull of the planets, with Jupiter, Saturn, Neptune, and Uranus having the greatest effect. The Sun's motion follows a somewhat regular pattern, forming a trefoil shape over certain periods, but it can also appear chaotic at times. The solar system is surrounded by the local interstellar cloud, and there are other interstellar clouds within 300 light-years, including the local bubble, a cavity or superbubble suffused with high-temperature plasma. These structures are part of the Orion Arm, which contains most visible stars in the Milky Way. Within 10 light-years of the Sun, there are few stars, with the closest being the triple star system Alpha Centauri and the small red dwarf Proxima Centauri, which has an exoplanet called Proxima Centauri b. Other nearby stars include Barnard's Star, Wolf 359, Lalande 21185, and Sirius. The Ursa Major moving group, located about 80 light-years away, is the nearest visible group of stars beyond the immediate celestial neighborhood. The closest star-forming regions include the Corona Australis molecular cloud, the Rho Ophiuchi cloud complex, and the Taurus molecular cloud. Overall, the solar system is a complex arrangement of celestial bodies, with the Sun at its center and various planets, dwarf planets, satellites, and other objects orbiting around it. The solar system is situated within the Milky Way galaxy, which is a barred spiral galaxy with a diameter of approximately 100,000 light-years and more than 100 billion stars. Specifically, the Sun is located in one of the outer spiral arms of the Milky Way known as the Orion Cygnus Arm or local spur. It is positioned around 26,660 light-years away from the galactic center, where the supermassive black hole Sagittarius A star resides. The Sun orbits the center of the Milky Way at a speed of approximately 220 kilometers per second, completing one revolution, or galactic year, every 240 million years. The solar system's path through interstellar space is directed towards the constellation Hercules, in the vicinity of the bright star Vega. The plane of the ecliptic, which represents the orbital plane of the planets, is inclined at an angle of approximately 60 degrees to the galactic plane. The solar system's location within the Milky Way has influenced the evolutionary history of life on Earth. The nearly circular orbit of the solar system, coupled with its relative speed to the spiral arms, means that the Sun passes through these arms infrequently. The spiral arms contain a higher concentration of supernovae, gravitational instabilities, and potentially disruptive radiation. Consequently, the relative stability of the solar system's position has allowed for longer periods of stability and the evolution of life on Earth. However, it has been suggested that the changing position of the solar system in relation to other parts of the Milky Way could be linked to periodic extinction events on Earth, although this hypothesis remains controversial. The solar system is located far from the densely populated regions near the galactic center. The gravitational influences of nearby stars in those areas could disturb the Oort cloud and result in an increased number of comets entering the inner solar system, potentially leading to catastrophic collisions with implications for life on Earth. Additionally, the intense radiation emanating from the galactic center might interfere with the development of complex life. Occasionally, there are stellar flybys in which stars pass within 0.8 light-years of the Sun, occurring approximately once every 100,000 years. One notable example is Scholz's star, which approached the Sun likely traversing the outer Oort cloud. The observational history of the solar system's position within the Milky Way provides insights into the factors that have shaped the stability and development of life on Earth, as well as the potential influences from neighboring stars and the galactic center. Throughout human history, the Sun has been revered and worshipped in various cultures and religions. Early civilizations saw the Sun as a deity or supernatural entity. In the first millennium BC, Babylonian astronomers observed the Sun's non-uniform motion along the ecliptic, although they didn't understand the reason behind it. It was later discovered that Earth's elliptical orbit around the Sun causes this variation in speed. Anaxagoras, a Greek philosopher, proposed in the 5th century BC that the Sun was a giant flaming ball of metal and that the Moon reflected its light. However, his ideas were considered heretical, and he faced imprisonment and death for his beliefs. In the 3rd century BC, Aristarchus of Samos proposed a heliocentric model, suggesting that the Sun is at the center of the planetary orbits, but this view wasn't widely accepted until Copernicus developed a detailed mathematical model in the 16th century. Advancements in observing the Sun began in ancient times, with Babylonian and Chinese astronomers recording sunspots. Galileo Galilei, using a telescope in the 17th century, observed sunspots and concluded that they were on the surface of the Sun. Arabic astronomers made important contributions, such as discovering the changing direction of the Sun's apogee. In the 19th century, spectroscopic studies of the Sun revealed absorption lines known as Fraunhofer lines, and scientists started to unravel the Sun's composition. In the early 20th century, the source of the Sun's energy was a puzzle. Lord Kelvin proposed a cooling liquid body, but it couldn't explain the Sun's longevity. In 1920, Arthur Eddington proposed nuclear fusion as the energy source, where hydrogen fuses into helium at the Sun's core, releasing vast amounts of energy. Theoretical work by Subramanian Chandrasekhar and Hans Bethe in the 1930s further developed the concept of fusion. In recent decades, numerous space missions have been dedicated to studying the Sun. The Solar and Heliospheric Observatory, SOHO, launched in 1995, provided continuous observations from the Lagrangian point between Earth and the Sun. The Solar Dynamics Observatory, SDO, and the Parker Solar Probe have contributed to our understanding of the Sun's dynamics and the solar wind. Other missions, such as Yoko, Ulysses, and Solar Orbiter, have focused on specific aspects of solar observations. Future missions, like the Indian Space Research Organization's Aditya L1 and CubeSat for solar particles, CUSP, aim to study the Sun's corona and magnetic fields. These missions, along with previous and ongoing ones, have significantly enhanced our knowledge of the Sun and its role in the solar system. The Sun's atmosphere consists of different layers, including the photosphere and the corona. The photosphere has a temperature of approximately 6,000 K, while the corona reaches temperatures of 1 million to 2 million K. The high temperature of the corona is not directly explained by heat conduction from the photosphere. Two main mechanisms have been proposed to explain the heating of the corona. The first is wave heating, where waves generated by turbulence in the convection zone, such as sound, gravitational, or magnetohydrodynamic waves, travel upward and dissipate in the corona, depositing their energy as heat. The second mechanism is magnetic heating, where magnetic energy is built up by photospheric motion and released through magnetic reconnection, leading to solar flares and smaller events called nanoflares. While wave heating was initially considered a possible explanation, it has been found that most waves dissipate or refract before reaching the corona, except for Alfvén waves, which do not easily dissipate. As a result, current research has shifted towards investigating flare heating mechanisms. In terms of the Sun's history, during the Archean Eon, about 3.8 to 2.5 billion years ago, the Sun was weaker and less bright than it is today. According to theoretical models, this weaker Sun would not have been able to sustain liquid water on Earth's surface, suggesting that life should not have developed. However, geological evidence shows that Earth's temperature has remained relatively constant throughout its history, with the young Earth being somewhat warmer than it is today. Scientists propose that the young Earth's atmosphere may have contained higher levels of greenhouse gases, such as carbon dioxide and methane, which trapped enough heat to compensate for the lower solar energy reaching the planet. However, examination of Archean sediments challenges this hypothesis, suggesting that the moderate temperature range during that time could be explained by factors such as a lower surface albedo, reflectivity, due to less continental area, and the absence of biologically induced cloud condensation nuclei. These factors would have increased the absorption of solar energy, compensating for the lower solar output. It's important to note that looking directly at the Sun with the naked eye can be harmful. Brief periods of direct observation may cause temporary visual artifacts and partial blindness, while long-duration viewing can result in retinal damage. Using light-concentrating optics like binoculars or telescopes without appropriate filters can also cause permanent damage to the retina. During sunrise and sunset, the Sun is attenuated, making it safer to observe, but precautions should still be taken. One optical phenomenon related to sunset and sunrise is the green flash. It occurs when light from the Sun just below the horizon is bent toward the observer, usually due to a temperature inversion in the atmosphere. This bending of light causes shorter wavelengths, violet, blue, green, to be scattered more, resulting in the perception of a green flash. In summary, the Sun's corona is heated to extremely high temperatures that are not solely explained by heat conduction from the photosphere. Wave and magnetic heating mechanisms have been proposed, with current research focusing on flare heating. The Sun's history suggests that the early Earth's temperature was likely sustained through a combination of factors including higher greenhouse gas concentrations and lower surface reflectivity. Observing the Sun directly without proper protection can be hazardous, but during sunrise and sunset, when the Sun is attenuated, it may be safer to view with precautions. Today, we embarked on an awe-inspiring journey to unravel the mysteries of our magnificent Sunday. From its fiery photosphere to its enigmatic corona, we delved into the mechanisms that heat our star and sustain life on our precious planet. As we explored the fascinating concept of wave and magnetic heating, we discovered that the Sun's corona reaches temperatures beyond imagination, powered by forces yet to be fully understood. The quest to comprehend the intricate workings of our celestial neighbor continues, and scientists tirelessly pursue answers to unlock the secrets of this cosmic furnace. Reflecting on the Sun's incredible journey through time, we pondered the epoch when our young Earth danced with a weaker Sun, defying the odds by fostering the conditions for life to flourish. It reminds us that our existence is intertwined with the intricate dance of cosmic phenomena, where delicate balances and serendipitous circumstances shape our very existence. But let us not forget that our exploration doesn't end with the Sun. Look up at the sky, where stars twinkle in distant galaxies, and marvel at the wonders that lie beyond our reach. The sky, far from being a limit, is merely the beginning. Humanity's insatiable curiosity has propelled us to explore the cosmos, to push the boundaries of knowledge, and to dream of what lies in the great unknown. As we conclude this enlightening voyage, remember that the mysteries of the universe beckon us to explore, to question, and to seek answers. Together, let us continue to unravel the enigmas of our celestial surroundings, venturing into realms yet undiscovered. Join us in embracing the notion that the sky is not the limit, it is a gateway to infinite possibilities. With each discovery, we inch closer to understanding our place in the grand tapestry of the cosmos. So, keep your eyes on the heavens, your minds open to the wonders, and let us venture forth, together, into a future where knowledge knows no bounds. Thank you for joining us on this cosmic expedition. Until our paths cross again, remember, the sky is not the limit, it is only the beginning.